and reduce the intake of very high dosage, because high dosage will back to the toxicity. So from here, yeah, we mentioned here in a dosage form available to the body, and then the searching keep continue. Yeah, we will still continue to make sure that we get the correct compound and with the less toxicity in the future. Right. So in the computational study, we need to do the ADMET. If you remember, I mentioned I think about ADMET last time, but we're going to have a look again. This is one of the example of the system or the programs that we can use pre-ADMET, meaning that before you want to do the complete testing, you can also predict it, yeah, predict the ADMET computationally. So what makes a good drug? Basically, there are many, from here we can see that many drugs fail in the clinical development. If you still remember the clinical part, the clinical 1, 2, and 3, yeah, if it's failed over there, mainly because of some of this reason. For example, the pharmacokinetics, yeah, that is actually huge. This is something that related to the bioavailability. Adverse effects, so it's still very high, meaning that it causing many different or trigger many other effects. For example, people who already take some medication like heart disease, high blood pressure, even what you call this something related to the blood problem. So it will trigger many different type of adverse effect. Yeah? The bad one that normally we are talking about. So this is why we need to look at into the just now. This is more on the computational that we have done previously, but now we have to look at the absorption and distribution. First, drug must be absorbed. So that's why there are different ways of introducing the drug. I think I mentioned before, oral, that is the most challenging because it entered to our GI, the gastrointestinal. Then anything from blood, intravenous. We can also have renal ikut daripada bawah through the anus, and the pulmonary. Yeah, so anything that related on the inhalation. So distribution is very important, where it will go directly. Yeah, so that's why, for example, anything related to asthmatic, it shall be directly through the nose or by inhalation. Then metabolism and excretion. Yeah, because it is very important that during metabolism, how it is actually being what you call this metabolite, yeah, and then excretion. Please excuse me because I need to answer some very important call. I'm very sorry I don't do this. Just a moment. Very similar with the molecular docking and so on, but this one, the application is just for ADMET, where we're talking about the toxicology. Yeah, so whether we can just do ADMET or ADMET, it depends. So now with the advances in computational program, so we can do all these things just by prediction, as the video just now mentioned. So let's see again. You may have seen this one in the video just now, or the earlier video. So we have to look at how the drugs enter into our body. Yeah? So now we are looking at the ADME first. First is actually it enter into our system, into the body, but then there are many challenges. For example, our skin. Yeah, our skin have a very what you call this, the barrier, the permeability. Not everything can penetrate our body. Okay, so that's why if we want to develop anything that related to dermatology, yeah, derma, maksudnya skin, so we have to make sure that it need to cross the lipid bilayer. Lipid bilayer, because we know that we have some kind of fats, so the drug have to penetrate that. What else? If we're talking about the brain also have the blood-brain barrier. Not all type of drug can enter directly. Yeah, so that is why we call it different type of entering into the body. Then the second, distributed by the blood to the site of action. So how it goes? It is very important where, for example, the vaccine, why they kena cucuk dekat sini. Okay, why certain cucuk dekat, budak-budak selalu cucuk dekat what you call it, dekat dia punya buds, yeah. And certain cases like ocular, I forget to mention, and the one is ocular. Ocular is anything through mata, yeah, because anything related to ENT, even from the eyes, can drop to the throat. Okay, so it is very important to see all these things and how it is actually being distributed, and later on where it concentrated. The concentration end up where. Okay, so it is very important to understand this, because later on it be metabolized and also will be excreted. Yeah, biotransform meaning that maybe from the big molecules, it will be cut into, I'm using a simple word, just cut. So then the metabolites will go at a certain places or certain area in our body, so that it will take the place. But some of the metabolite as well can induce or menyebabkan adverse effect. And finally, anything that go inside to our body, it shall be removed, right? So kidney, it normally end up at the kidney, and kidney then remove them, yeah, the metabolite from the body. So that's why take it very exact, the easiest one. So normally, if we take a vitamin C, yep, and then with vitamin C having this kind of problem, it is easily degrade to something else. Yeah, so that's why right now they are put the ester. They call it ester C. It's more stable, and then there are many new kind of vitamin supplement that they add up also vitamin B, vitamin A. Normally vitamin B, yeah? And if you can smell that vitamin B, normally there is kind of smell. Anak saya cakap macam bau lipas. Okay, but normally if you take something like that, your urine will be slightly orangey or very yellowish. Okay, that is actually the metabolite as well that being excreted. So this is the pharmacokinetics that what I showed to you earlier, and then what we need to understand is the spam analogy to drug discovery. It's just like something spam, your email spam. If you put something rubbish in, rubbish out, basically normally what we say lah. Yeah. So that's why if we put all the crude extract, we are not that sure which one is the correct drug. So that's why in this time we need to find what we call as the active compound. Yeah, tongkat ali. Dia ada satu active compound. So same as well for the anti-malaria. For example, people use the artemisinin. Yeah. What else? This is the issue with the natural product. Sometimes the compound cannot work alone, so it need to be in like kind of a consortium, right? So I'm just gonna go directly to the discussion. Multi-objective optimization, it is very difficult. We want to have good permeability, meaning that it can penetrate the cell, high activity, low toxicity, and then at the end we're having problem with the solubility, but at the end maybe only very few drug can be as good as what we want. Yeah, so that's why there are many failed cases. So why people start to go into the computational toxicology? Because I think from that video just now you saw that it's very expensive to use a small animal and also the large animal. So large animal, for example, they use cats and dogs, or even monkeys, yeah, being used. So we try to reduce the usage of that. So that's why we can look at all those property of the drugs through the computational biology. So I'm not going to explain because some of the word I have mentioned before. Renal or hepatic clearance. Renal maksudnya macam buang air besar tu, and hepatic is anything that related to the kita punya liver jugalah, dan juga what you call this buah pinggang. I think this one also mentioned. We're going to look some of it. Now, prediction of toxicity is also very challenging because we cannot just determine everything through computational work. Yeah, so some of the work normally will be dated back from the QSA, because QSA means structure activity relationship, and the activity must be already done in the laboratory. Yeah, so that's why we got the information. But something, if there is no experimental work yet, so certain kind of the new one, I'm not working yet on this part, but I hope that I can work on this in the future, is the additional of the functional group will then enhance the information that can be put in the database. So that's why QSA involve biology, chemistry, and statistics, and also there are certain rules. Okay, I think this one again, one of the big issue, only 10% drug candidate enter to the clinical trial, but one I think I mentioned big issue just now due to the poor oral bioavailability. Okay, so bioavailability is actually one of our focus discussion for today. Yeah? So this one is what you saw just now in the video, how it enter into the system. First, this one, absorption, then where it goes. Okay, so to degree to which a drug or other substance becomes available to the target tissue after administration. I think last week's lecture, I did mention about we can control with certain type of delivery method. Yeah, for example, the drug we can conjugate on the certain nanomaterials, and then when it enter into the system at certain pH, then it start to open up. Yeah, I will give you the information shortly later. This is the lipid bilayer I did mention just now. To penetrate this is not easy. Okay, so that's why most of the drug have to be formulated. And now we are talking more into the nanomedicine, or at least nano formulation, so that it can pass through the water layer and then top bottom layer of this lipid. Lipid is actually lemak. Okay, so that's why drugs can be delivered because it is a bit lipophilic around here. But then you have to we need to do some calculation. We need to put some what you call that. Suddenly I forget the word. I mentioned later on. Tua ni selalu lupa. Okay, so that's why some of our formulation we can also put cholesterol, and in this case we also have worked with the lipid bilayers, the simulation of lipid bilayers. For example, we work on the ibuprofen. Have you heard about ibuprofen? No, it is NSAIDs, non-steroidal anti-inflammatory drugs, yang sakit-sakit lengan-lengan lutut tu ya. Selalu kalau orang-orang tua, mak-mak, nenek kat kampung selalu sapu je minyak-minyak panas dia cakap. It's not good. So what happened is right now there are many development of ibuprofen. So they make it into hydrogel, and then the hydrogel with up to 5 to 10% percentage of ibuprofen. Yeah, and then that one is not it's not hot as well. It's actually cooling. It can be in terms of patch, or it can be just in terms of what you call this. Just a moment. Okay, if you can see from here, because I'm an athlete, so memang hujung-hujung ni kerap pakai. This is the example of ibuprofen. Yeah, this is quite high, about 10%. If you can read here, I think here, 10% volume per volume. So in our work, we also develop that, where we use palm oil ester, yeah, to bind that. All right. We can also do the computational work here. Blood-brain barrier, this is some of the works that been carried out. I mean, some of my friends is working right now, particularly, I think I mentioned before about the Alzheimer, yeah, because you want to, tak logik lah you nak pergi cucuk kat kepala kan. It's very hard, but there are certain drugs that can penetrate the blood-brain barrier, because it have a very tiny gap, so that it can enter into our brain. Now, drug transport into the membrane is not a straightforward. Yeah, that means it have to go through the aqueous and lipophilic barrier. I think in the the lipid bilayer just now I showed that first they have to go through the water, then what you call this, the lipid or the cholesterol. If you have like a thick cholesterol, like jenuh dia nak masuk, then again back to the water. So it's not a direct process. Sometimes they have to mingle, and there are many different barriers. This is something that you will study more on the biological activity from this QSA. So this is one of the QSA equation. Yeah, we have to know the lipophilicity, the polarity, and then the electron, and also the steric effects inside that. So we call it as a random walk. Right. So this is what you basically, I want to wrap up our study before. You remember that this is one of the modern drug design from zanamivir to oseltamivir, which is actually based on the neuraminidase. The enzyme is called neuraminidase, and this one is actually the design of these two drugs, basically based on this and acetyl-neuramidic acid. So this is actually how, if you want to look at the docking between the crystal structure and then the interaction with the amino acid surrounding this receptor. Okay. Then, of course, it's not limited to that. As a chemist, we need to understand the mechanism. Yeah, so based on this, they found that the sialic acid or this OH is very important in this neuraminidase enzymatic activity. So based from that, they start to look into each from here, and then try to get into the final position. So you all suka-suka hafal, nak keluar exam, bolehlah saya bagi macam ni. Minat? Boleh kan? Alright. So, tak suka seronok lah mechanism. Okay, and then based on that, they start to do the modification, because one, the neuraminidase or the flu enzyme also start to do some mutation. And another thing is based on the claim from the patient, certain of side effect. I think the most common one is nausea, yeah, pening, muntah, yeah. That is very common because our body, the pathway start to do some changes. So based on that, they start to change, and this is something that organic chemists like to do. At certain position, they start to change into a different functional group. So you can also see that number 3, first compound synthesized by Einstein team. Okay, but then it's a weak activity, and then they keep doing some changes until at the end they come into the second modification. Okay, and one at the 6, they start to put the azide intermediate to synthesize the 4 and 5. Only they come to the synthesis, a complete synthesis route of the zanamivir. Okay, so it's not easy process from 1, 2, 3, and 4, and 5, 7. Yeah? And you can see as well the location where it is actually being here, what you call that, modified from this, here, and so on. Okay, so same as well. I'm not gonna repeat all the information, but this is a very new that I would like to share with you. This is sumber daripada berita harian. I hope, I'm not sure if there are any international student, but if you do have, you can. This is a very basic info. Now, the drug baricitinib need to be used with the remdesivir. Only then it can be used to treat the COVID-19, but it depends on the stage. Yeah, normally stage 1 and stage 2, based on the study overseas. Malaysia do not have that complete study yet, but later on the government also proposed to the usage of molnupiravir. Yeah, and this is actually proposed for the stage 3 or stage 4. Okay, so based on that, if you compare the drug structure, oh ini kalau bagi quiz ronok ni. Now, it's a very simple thing. If you look at this, you know, N is actually representing the nitrogen, O, oxygen will be red, and then you have sulfur as well as. So based on this, you can also determine whether this kind of drug fulfill or violate the Lipinski rule or not. So you can see this one is the baricitinib. So it have huge number of nitrogen, yeah, nitrogen atom. Then for this one is the remdesivir, and this one is quite small actually. This is the molnupiravir. So you can see that there are many places that we can do some modification, and each drug give you a different activity. But in certain cases, they propose a dual drug. Yeah. So to end of our lecture, because if too many theoretical, it will be hard as well for you. I think at this point, I want you to know that whatever that you have learned, it can be applied and not limited to just drug design. I mentioned one previously in when we look at the peptides, we can move into the food industry, for example. Yeah. The antifreeze protein. Another one I also showed you that we can also use to design a biocatalyst, and that is actually more into my expertise, working more on the protein engineering. We engineer the protein, particularly in my work, focus on the metalloenzyme. We try to put the metal into certain place in enzyme. Other than that, this is also something that I established way back in 2005. Yeah? Dr. Alif is actually my first student working on the computational colloids. So colloid is actually very important in Malaysia. Our drugs, normally colloids, even our food, there are many colloids. Yeah? So what we are looking at here is working on the nano emulsion, so that we are working on something very small. So here, I'm not going to go into detail. This is something that you're going to learn, the MD, coarse grain and Monte Carlo simulation. So we can use this in order to do the final formulation. Yeah, for example, our work, we started with application for cosmetic and cosmeceutical. Cosmeceutical, that means for the dermatology, yeah, untuk anything yang related to the kulit, but have a nutraceutical activity. Yeah, for example, we are the usage of tocopherol, tocotrienol, and this is something actually from the palm oil. And then I did mention about we are using also the ibuprofen. Okay, for the pharmaceutical, currently my team, Dr. Azlina Liza, working more on this blood-brain barrier. Okay, we also work on the agriculture. So this is for pesticide, the delivery of pesticide. Okay, so we are working on the nano emulsion. So what we did from here, I hope you can hear the music. This is work by Dr. Alif. Previously, when we have the surfactant, yeah, this is the word that I was looking just now, surfactant. Okay, surfactant is very important. Dia nak menyanyi pula. This is what we predict based on theoretically predicted by Davis way back in 1994. So we can see that we can, you know, with the different amount of surfactant, oil and water, at certain percentage, we can show that it looks like kind of lamella. Okay, so lamella is actually we prefer if we want to have a, for example, like to have a how to say this, not fast release, but macam kita tekan dia pecah. Okay, something like that, yeah. So the direct release, something like we can say, but some we also want it to be like kind of in the spherical shape, yeah, this so that this spherical shape, it can penetrate the cell. So in a very small size, in normally 100 to 150 nanometer. So what we can do is we can control the release of the drug. Yeah. So based on that, this is also another student working on this. This is actually ibuprofen. You can see that at the end, we can see that the ibuprofen, this is the palm oil ester. At the end, we can see that the ibuprofen is found at the outer layer. So we then suggest that this one, the ibuprofen molecules at the outer layer, suggesting that it is an instant release. So that's why if we want to use a certain type of drug, we need to control it. Yeah, like ibuprofen yang sakit lengan-lengan lutut, we need to make it a fast release, instant. But for the cancer drug, we want it to be slow release, control. After 6 hours, how many percentage to be released and so on. Because the issue, if you give everything abruptly at the same time, so it will also attack the healthy cell. You can also see other, what you call this example. Yeah, for example, we run up to 500 nanosecond and we can see this is actually the ibuprofen. Yeah, the yellow one. We can see is actually, sorry, this one is diclofenac. It's actually just at the outer layer as well. And the most important, it also gives a very stable micelle. So right now, to those girls or ladies, shampoo yang baru, semua dipanggil micellar. It's actually back into this kind of basic formulation. Okay, so we can also use a different type of simulation. This is the molecular dynamic. Yeah, you can see also this one, the yellow one is ibuprofen, but with this one use a coarse grain MD simulation. So you can see where the ibuprofen goes and you can monitor later on. I'm not going to go, this one is what we did with the coarse grain MD for lipid bilayer structure. We can see that this is actually the penetration of the drug from the top into down here. So this is first we have to model the PPC, the bilayer, and then this is how the drug penetrate into the system. Don't worry about this one. I'm just going to give you some information. So same as well, we can use in different ratio. So once we understand different ratio, then only we use that in our in vitro simulation. So this is actually one of my project together with the Harvard School of Public Health, the TH1. This is one of the most famous one in of course in the US. So we went there and we did lots of work. We are looking at some the diseases that are related to the smoking. Okay, so we are hoping that in 2045 Malaysia is a smoking free country. Okay, so first we are looking at the nanostructured aerosol particles. How can we design? And then of course, I think I mentioned just now, by using some of the formulation, we can conjugate many things, peptides, fluorescent agents, so that we can monitor where it goes. And we're also working on the aerosol droplet nano delivery. So this is actually very unique. As far as I'm concerned, until this year, we are still the first group that working on the pulmonary of pump-based drug for the cancer purposes, yeah, mainly for cancer purposes. So that's why we can work with the Harvard University together with the University of Malaya. So we just concluded this project late last year. So overall, if you like to see, quercetin is actually very the flavonoid is very what you call this hydrophobic. So instead, so we have to mix up with the formulation, including the different surfactant that we need to study, and different composition of oil and water, do lots of pH, and then we need to go into the in vitro study, and at the end, of course, we need to do the in vivo. We put the aerosol into these mice. Yeah. Other than that, we also doing something very new with the reticular materials. In your textbook, not yet. Even your syllabus is not yet. They explain about reticular materials. So this is why we're working directly with the Berkeley, Professor Omar Yagi, with Berkeley. So in Berkeley chemistry department alone, they have 30 their alumni or their current researcher Nobel Prize winner. The recent one was Professor Jennifer Doudna, in the gene editing. Yeah, so in our work we can also use computer in order for us to look at the enzyme when you put in the MOF is the metal organic framework. It's like kind of cage, or it also can be like kind of a long tube. Okay, and then we can run like asymmetric reaction. We can also do many different type of bio-inspired MOF. So this is a very challenging. We're also working with the Madrid, and this is ICMM, Institute of Science and Material in Madrid, under the National Spain Research Council, and also the Royal Scientific Society Jordan. So my student went to Berkeley in 2019, 2020. I supposed to be there, tapi dah tutup. I mean COVID. Now my student 2 weeks in Madrid, 2 months in Madrid. I think dia akan pergi 2-3 kali, Zura. Then Umar just also went to Jordan for 3 months. So Zura ni lah dia kaki bola rasanya. So she will enjoy Madrid. Okay, so this is actually one of our works that been cover page for Dalton transaction. This is one of the the hardcore lah, which is one of the best journal in particularly for the material. So we managed to get into this cover page. It's not easy, yeah? It's never easy. So if you can see here, this is, we start with the computational. This is the ZIF 8, nano ZIF, small, and we this inside the green one is actually the drug, and here is actually homing peptides. Actually, peptide is being conjugated, and the peptide acts like kind of a GPS. It will only go and target the cancer cell or cancer environment. At the right time, it will break and it will release the drug. Okay, so now we are working with many different type of reticular materials. In fact, some we work on our own. So of course, that's current work, and the future work we are working right now. We just get approved from JICA and SATRAX. This is actually a big project between us, UPM, and University of Tokyo and Nagoya Institute of Technology. So now I'm working on this potential of anti-dengue, but based on the curcumin. So we have modified the curcumin, about maybe 300, almost more than 300 new curcumin derivative, working with Dr. Siti Munira. So now we want to dock our curcumin with different type of dengue proteins. Okay, so this is a new work, and I also like to now invite if any of you interested to do your PhD in Tokyo University, but you have to do master first, so we can propose your name over there. I just received a message just now that they're asking my student to go to the University of Tokyo for research attachment. So in case some of you going to do a final project, I know that people always ask me because of this pandemic as well, I stopped to do anything that related to the lab work, but we focus more on the computational, will be easier. So currently we are heavily on this molecular docking and dynamic simulation of dengue protein with curcumin derivative. And we also start to enter into a new phase where we want to involve in the AI, the artificial intelligence, where we like to move into the machine learning. Other than that, I also received another project with the Sukuk Kementerian Kesihatan Malaysia, working on the MD simulation of aerosolized nanoemulsion for pulmonary drug nano delivery. So we are also trying to work on the what you call this. This is basically COVID-19 or cancer. And other than that, we also hope that still this is something totally very challenging, working on the computational with the metal organic frameworks. So I think that's all from me for today. Yeah, we can conclude that. I do hope that if you, yeah, now basically I would like to open for anything that you want to share based